Okay, thank you very much for the invitation. I'm a bit sad that I didn't cross the Hudson River to come to the Graduate Center, and mostly I'm happy that we're not gonna have the cheese and wine. Okay, but I hope Olga can send something over to my house.
For sure, from Montreal.
Oh, you're in Montreal, okay.
Yeah, you have to pay customs.
Okay, so, oh, all right.
Please.
Yeah, okay, I found it.
Please mute yourself because there are some sounds.
Yeah, no, I think it was my buttons that I haven't pressed to the screen first before. Anyway, so let me start with some background. So I guess you all know by now that that's a big question of Tarski around the 40s, that whether the first order theory of non-abelian free groups is complete, and that was answered in the positive by Slil and Olga and Alexei independently. And actually in a strong form, that this chain of natural bendings is an elementary chain. So all non-abelian free groups have the same first order theory. So following my supervisor Anand, I will denote this theory by TFG, the theory of, I will call it the first order theory of the free group, or the theory of the free group, which might sound confusing to non-model theorists or to non-logicians, because there are, of course, many non-abelian free groups. But that's a shortcut. That's the way we refer to it. And it's pretty obvious if you're a logician that it refers to this unique theory. And an extremely profound theorem was proved later by Slil that this common theory is stable. And that was quite surprising, very surprising, for the following reason. So stability is inextricably connected with a notion of an independence relation, which in model theory we call forking independence. And usually when you have a natural theory, so the prototypical examples, let me say, are algebraic independence, or in algebraically closed fields, or linear independence in vector spaces. And as the non-abelian free groups or free groups have been studied very thoroughly by geometers and group theorists and topologists, there was no use of a similar independence relation, right? So it came as a surprise that such an independence relation exists and is justified by this stability result. Moreover, so more structural results, model theoretical results around this theory was Poisson, even before the answering of Tarski's question, proved that F omega is not superstable. So stability, apart from being connected with an independence relation, is also connected. Actually, it was discovered by Saharon-Shelah in his classification theory. So it was the first and the most important dividing line. The second dividing line is superstability, that says that not only you have an independence relation, but with this independence relation, you can define a rank. In particular, when you're superstable, you can define the U rank or Laskar rank. So this theory is not superstable. Now, there are more structural results which are negative, or for example, the free group is not equational, something I gave a talk about last year at CUNY. And that first was proved by Slil and then by Isabel and myself.
So you gave a simple proof, right?
Yeah, it's a very simple proof. Selah's proof is very complicated. Our proof is very simple, and it extends to all non-trivial free products apart from Z2 free product with Z2, the diedral group. Mm-hmm. But what's important for this talk is that TFG has not the finite cover property. That's a property introduced by a famous logician, Kistler, in terms with what is called in logic Kistler order, which is another way of classifying first-order theories. But what is important for us is that given stability, this is equivalent to saying that we can eliminate the infinity quantifier. So given a formula, phi xy, independent of the parameters y, we can say that if you have, we can assign a number, a natural number n, and you can say that if you have more than n solutions, then you have infinitely many. So this is what NFCP means, assuming stability. So all these results are, if I want to place them in a context, I would say these are results in classification theory. Now, moving to almost perpendicular direction, but with connections with classification theory, we can find geometric stability theory, which is, it's a context mostly developed by conjectures and results of Zilber. This is how it started. Like the main conjecture, his main conjecture there, which is known as the trichotomy conjecture, was that if you have the main building blocks of an Aleph-1 categorical theory, which are a strongly minimal set, to a strongly minimal set, you can assign a pregeometry. And the trichotomy conjecture was saying that this pregeometry could either be trivial, so you have the empty set, or a vector space, or an algebraically closed field. And only these three cases can appear. Now, Hrusovsky refuted this trichotomy hierarchy. And from his refutation, the ample hierarchy emerged. So the ample hierarchy, which is connected with Zilber's trichotomy conjecture, tells us nowadays, like a more modern interpretation of this, tells us how complicated forking independence is in a stable theory. So you can place a stable theory in this hierarchy, say the first level is not being one ample, and at this level you find abelian groups and vector spaces. In the second level, which is I'm not two ample, you can find Hrusovsky's counterexample, the refutation to Zilber's trichotomy conjecture. And then actually the hierarchy does not collapse, but for each level of the hierarchy, recently in 2014, Katrin Tant and Amador Martin Pizarro, Andres Baudish, and Martin Ziegler proved independently that for each level of the hierarchy, you can find a theory that is not an ample, but not n+1 ample. So the hierarchy does not collapse. So it has this technical definition, but that I don't want to explain how this came up, but intuitively, this is what it means. It kind of says how complicated this forking independence is that is inextricably connected with stability. So now since, so since the free group is stable, we can place it somewhere in this hierarchy, right? So first Anand proved that the free group is too ample, which is the same as saying is not CM trivial, what I have written down here. So the free group is too ample. And he conjectured that we can place it in the third level of the hierarchy and prove that is not three ample. But this turned out to be wrong. So actually, the theory of the free group is n ample for all n. So forking independence in this independence relation is as complicated as possible. And here is good to know, like that when Anand proved that if a first order theory interprets an infinite field, which I'm going to explain what interprets means, then it has this property. Then forking independence is as complicated as possible. Then the theory is ample. On the other hand, that's not an if and only if. That's not a characterization of n ample for all n, because Evans and other model theorists proved that he found actually a concrete example of an ample theory that it doesn't even interpret an infinite group.
Is it like natural theory?
It wasn't a natural theory. It was it had to do with graphs, but it wasn't some natural graph. Mm-hmm. So it wasn't a natural example. But in principle, the conjecture was that TFG, the theory of the free group, does not interpret an infinite field. So forking independence could be as complicated as possible, but not because of an infinite field. And for this result, I want to talk to, so this conjecture, I confirm this conjecture, and this is what I want to talk about today. That was the motivation. This is how the question comes up to model theorists. Now, if you do not work in logic, maybe definability and interpretability of an algebraic structure might sound strange, because you would say, okay, I have this group operation in a free group, so how can I possibly define a field using this operation? But when we talk about definability, we don't necessarily mean that the group operation of the field will come from the group operation of your structure. We just mean that there exists a formula whose graph would be the group operation or the field or the two groups operation. So as an example here, if we start with a field, an arbitrary field, we can define the general linear group of 2 by 2 matrices, but we have to move in dimension 4, in 4 tuples. So how we're gonna define the domain? We're gonna say I have a quadruple that x times w minus y times z is not 0. And if I collect all these quadruples, then I will consider them as my matrices. And multiplication is defined as like in the natural way. So that's the graph of my multiplication of matrices, right? So this dot here is the dot product, which is a shortcut for using the multiplication of the field and the addition of the field. And finally, the neutral element is defined naturally like this. Okay, so this is a bit of explaining a bit of the complexity of the problem, that when we say find an infinite field or find a structure inside another structure, we don't necessarily mean that the multiplication of your field will come from exactly the multiplication of the free group, right? It could be just a formula, and that's the complexity of the problem. This adds to the complexity of the problem. And in addition, we have to account for a complexity that comes from quotient structures. And this leads us to the notion of interpretability. So if I want to define it intuitively, some structure M is interpretable in other structure N if I can define N up to definable equivalence relation. And of course, when you work with algebra, with algebraic structures, that's a pretty natural, it's a pretty natural construction as you take quotients all the time. Only in this case, we have to make sure that the quotient is definable. The equivalence relation is definable. So for example, PSL2Z is interpretable in SL2Z. That's very natural. And more generally, when we have a group G and a definable normal subgroup, then the quotient is interpretable in G. Okay, so that's how this adds an extra layer of difficulty, as we need not only to prove that there's no definable infinite field, but is not definable up to an equivalence, up to a definable equivalence relation. And like if I want to abstract it even more generally, and this is a construction that it's essential in model theory, and it appeared in the classification theory of Sachar and Schelach for different reasons for his project. Whenever I have a first order structure in general, not just a group or a field or whatever, then I can collect all the definable equivalence relations and define a new structure, which is now multi-sorted. This means that my domain will have multiple sorts. That is not just the real elements of M, but also elements as equivalence classes. So for example, if I have a group, I would always have conjugation as a definable equivalence relation, right? So I would have one sort for my real elements, one sort for conjugacy classes, and different sorts for different equivalence relations that I can define in this particular group. And together with class functions that would connect my real elements with my imaginary elements. I could call them imaginary elements. So now this construction is known as passing from my structure M to MEQ. And given the definition above, it's pretty natural that if X is interpretable in M, X is interpretable in M if and only if is definable in this new multi-sorted structure that I have added my equivalence classes as elements. So this is a two-step kind of a two-step justification of what I'm trying to prove in the free group.
Sorry, so you add all definable equivalence relations, right?
Yes. Yeah.
Okay.
Yeah. Okay, and that, as I said, was like a two-step. First, we're considering definable fields, and then we have to go one step further and consider definable fields in MEQ, in this new structure where I have added all my equivalence classes as new elements. There were some partial results until the full result. So the first by Chloe, Anna, and myself and Catherine, that we prove for a special class of formulas that I'm gonna say something more later, as I don't want to define what foreign is. Let me just say is a special class of formulas. So for a special class of formulas that they have this property, they cannot even define, they cannot even be the domain of an interpretable abelian group, this special class. And the second theorem, which I borrowed, of course, a lot in this new paper, was a paper we had with Ayla, that we proved that there's no infinite definable field. So we had to pass from no infinite definable field to no infinite interpretable field. So no definable, even if you define it up to an equivalence relation. And I want to give you now, that's an example, that's an instance of the first theorem here, this proposition. So this is a formula. I have a formula with parameters in Fn, the free group of rank n. And the special property it has is that if I see its solution set in Fn plus 1, it gains an element. So I have the solution set in Fn plus 1 and the solution set in Fn are different. So it gains it gains an honest element of Fn plus 1 that does not live in Fn. So this is a special class of formulas that have this property. And the proposition that actually dominates the full proof, it's a very special case, but we will see that how it dominates, the idea of this proposition dominates the whole proof. So we can prove that this formula cannot even be given definable in abelian group structure. So the proof is pretty straightforward and very, very nice, amusing, I would say. So suppose not, and suppose there is a formula here that I have denoted by O plus that defines the graph of an abelian group. And phi of x is the domain of that group. Now, from the hypothesis of the proposition, I have an element that belongs to my domain, which is a true element of Fn plus 1, and not what I call an honest element that does not live in Fn. And I tweak it a bit. So I tweak it a bit using an automorphism, fixing Fn. I can change En plus 1 to En plus 2. And now this element B that just has En plus 1 with En plus 2 changed also live in my formula just because I used an automorphism and fixing Fn. And because automorphisms respect formulas, my B also live in the domain of my group. So now I have two elements of my alleged abelian group, and I can add them using the abelian operation I claimed I have. So I can add them, and this will give me a new word, a new element that would also be an honest element of Fn plus 2, because if not, I could use the inverse of A and prove that B also is in Fn plus 1. So Z, this element Z, is also an honest element of Fn plus 2. And now I'll do the following trick. I'll have this automorphism that fixes Fn. So fixing Fn means that I fix all the parameters of phi and the abelian group operation, the O plus. And I will exchange En plus 1 with En plus 2. That's a pretty straightforward automorphism of Fn plus 2. And I will apply this automorphism to my formula, and my addition A plus B equals Z, okay? But what this automorphism do, it just changes the order of the sum, the order of the addition, right? It changes that from A plus B, I get B plus A, but since the operation is abelian, Z should be equal to F of Z. And now, oops, we have a contradiction of normal forms, okay? Because like, if I have an honest element of Fn plus 2 and I exchange En plus 2 with En plus 1, I do not get the same element. So that was like a very simple, nice trick, works for this special kind of formulas. And it just depends on normal forms. Nothing here heavy. Okay. And as you will see, this kind of idea is dominating the whole proof, even the hard cases. Now, there are, of course, some predicaments in some difficulties in generalizing this trick, which I will call the non-commutative argument. First of all, there exist infinite abelian groups, which are even subgroups. So actually centralizers of non-trivial elements are isomorphic to Z plus. And let me mention here, because this answers a question of Malchev, that in this work with Katrin, Annan, and Chloe, and independently Olga and Alexei, have proved that these are the only proper infinite proper subgroups, centralizers and their subgroups. Nevertheless, let me close this parenthesis. So we have infinite abelian subgroups, so the argument fails miserably for this class of formulas, and we have to find something completely different for that. Second difficulty, when we try to pass from non-definability to non-interpretability, we have to take consideration conjugacy classes, for example, or other equivalence classes. But conjugacy classes are always present in groups. Always conjugation is an equivalence relation, and actually in the case of a free group, it cannot be eliminated. So there is no definable choice function that would give us, that could eliminate conjugacy classes. Now, what happened if we apply the same argument for conjugacy classes? So suppose now my elements are not just words, but these brackets are conjugacy classes. So if it could happen that when I add A with B, it gives me this product, En plus 1 times En plus 2, right? And now if I apply my argument, so if I apply an automorphism, I won't get a different conjugacy class. I will fall into the same conjugacy class, right? If I exchange En plus 1 with En plus 2, it will give me the same conjugacy class. So there's no contradiction in this case. So this trouble here is not as severe as the previous point. We can find a remedy and still apply a similar argument as before for conjugacy classes and even the rest of the equivalence classes that I'm gonna talk about later. But one problem that I guess it's obvious to everyone is that this argument worked for a very particular reason, because I could use automorphisms. Automorphisms that I knew they would fix my formula, and I knew kind of how they will change my element, my nice element. But in principle, if my formula does not gain an element, and for example, an example of that formula is centralizers. A centralizer of a non-trivial element is an example of a bad formula for us, then of course I cannot use automorphisms, right? They will change the solution set in a way I cannot control. And we will see that if we take up the case of the centralizers, that they need a completely different argument, then I can recover a non-commutativity argument, but in a very kind of very technical and hard way. So let's first take care of the centralizers. And the case of the centralizers is something that worried me about this talk, because it falls into the domain of model theory. So taking care of the centralizers, I based my proof in a technical result we have with Daniel Palassin. And here is where we use the ranks in model theory. What I said, superstability allows you to define ranks. What we have here for the centralizers is as follows. So I want to prove that a centralizer is a pure group in the sense that all the induced structure it gains from the ambient free group is nothing more. So it doesn't get any more definable structure than the structure I can define by its own group operation. If I prove this, I know then that in abelian groups, I cannot, in Z plus, I cannot define an infinite or interpret an infinite field, and I'm done. And this boils down to prove something model theoretic. It boils down to prove that centralizers have U rank or Laskar rank 1. So they are super stable of Laskar rank 1. Why I mentioned this? Why this makes the proof easier because it allows us to concentrate on the, not in the Cartesian product of the centralizer, because as you saw the example of definability before, I could define GL2K in the Cartesian product of power 4, right? So in order to prove that there's no field definable in a centralizer, it could be that a field is definable by using like a Cartesian power of some dimension, of some power. But here, model theory allows us to restrict ourselves in dimension 1. Just prove, in order to prove that my centralizer has Laskar rank 1, I need to prove, that's equivalent, that every infinite definable subset of my centralizer is generic, where generic means that finitely many translates of this set cover the centralizer. There is a caveat here. When I'm dealing with ranks, I need to work in a very large model we call saturated models. I can avoid that using an FCP. Okay, that was a bit of a totally like model theoretic argument here. I hope I haven't lost many. So again, what I need to prove is that in order to prove that my centralizers are pure groups, I need to prove that every infinite definable set finitely covers the centralizer. And that's the only step that we use the works of Slil and Olga and Alexei in order to prove that if I have a definable set, then it contains an arithmetic progression up to a finite set, hence it is generic. So, okay, this part of the proof is not obvious. So one needs some non-trivial tools here to prove this. Nevertheless, this is this last argument proves it, and together with our theorem with Daniel, this proves that centralizers are pure groups and they cannot interpret an infinite field. So no infinite field lives in centralizers, and this takes care of centralizers. Now, how do we deal with conjugacy classes? That's easy. This takes just a nice idea, and the same argument holds, the non-commutativity argument. So how does this work? Instead of taking the sum of two elements of, again, now the idea, what I have written here works for my special class of formulas that gain an element in a higher ranked free group, okay? So I'm recovering the argument I used, but now for conjugacy classes. So how it works, instead of adding two elements, I add as many as I want. I add k many. So why we do this? Because now we have the full power of permutations. Instead of just permuting en plus 1 with en plus 2, we have the power of k factorial permutations, and this indeed changes also not only words, but one can prove that it also changes conjugacy classes. And we can also give like a bound that it's important to know how many conjugacy classes you get if you use these kind of permutations. This will be important later, that we can change it a lot, or at least the number of conjugacy classes. It's important to show that the number of conjugacy classes increases as k increases. Right, and now that's the core of the idea, that we abandon special formulas and we have to deal with formulas that are not special. So we have to deal with a general formula. The idea here is to replace first order formulas with algebraic objects, which are called towers. And I will show you why. I will show you the connection, but for the time being, I will show you how first-order formulas are connected with these objects that we call towers. But for the time being, let me define what towers are. So towers are groups that are constructed in a particular way. They have surface floors and abelian floors, and we build them by, we have a nice base of a free group, and we add either a surface floor or an abelian floor consecutively. So what is a surface floor? So a surface floor is, so a group G has a structure of a surface floor if we have a central, if it splits as a graph of groups, where we have a central vertex whose vertex group is a surface group with boundary, and it is connected to the rest of the vertex groups with Z edges connecting it through its boundaries. So this semi-topological, semi-group theoretic picture is quite regular. Like it's quite regular in this kind of topic. So this just says that this vertex that looks like a surface is a vertex group whose fundamental group, whose vertex group is a surface with boundaries, and it connects to the rest of the vertices through Z's edges, infinite cyclic edges. There are some extra conditions, like that you need to have a retraction from G to from the whole group to H, which is the free product of the non-surface vertex groups. But that's kind of technical conditions that are used throughout the solution of Tarski's question. And okay, it doesn't make now any sense to try to justify why this is constructed the following way, but that's the definition. And much more easy, one can define what is an abelian floor. So recall a tower is constructed by using surface floors and abelian floors. And an abelian floor, it just, so a group G has a structure of an abelian floor if it is an amalgamated free product where E is a maximal abelian subgroup of H and is connected to a vertex group, which is the direct product of E with some free abelian group. So this is pretty straightforward. Okay, and here is the definition of a tower. So a tower is, as I said, it has a nice bottom, a nice ground floor of a free group, and we add consecutively either surface floors or abelian floors. So yeah, that's a tower. And how we connect towers with formulas. So that's the theorem by Slil. I'm pretty sure there is a counterpart or there is some analogous theorem in the work of Olga and Alexei. But so we connect first order formulas with towers as follows. So to each formula, we assign finitely many towers. So towers can be seen as groups with extra, like with information about how to build them. And so in particular, we can have we can see their presentation. Actually, towers would be finitely presented. And we can see in their presentation, we can prescribe elements that would, we can prescribe elements, the X actually elements that will be connected with the variables of the formula in the way that is explained below in the two properties of the definite envelope that are explained below. So the first property is that if we project the variables or the elements of the towers, they cover our original formula phi. Okay. So the value of a morphism from GI, say to F, to the free group F, if we see where it sends X, so these solutions, these morphisms, these images of morphisms cover our original formula. And second property, which is the important property for us, is because just the first property would be easy. Like we could take just X equals X, just a free group, and this would cover all possible formulas. But the second property, which is important, is that we have some understanding of the solution set of phi through test sequences. So the Diophantine envelope is not too big, like it's close to the formula as some geometric object. And this is what we gain actually moving to the Diophantine envelope. We gain that we have some intuition about the solutions of the formula. We have some algebraic intuition. We know that test sequences belong, if you project to the right elements of the group, belong to the formula. Now, test sequences are quite hard to explain in full generality what a test sequence is. But I can give you like a very small, minimal example of a test sequence. So for the simplest of towers that we don't have any floors, just the bases, which would be our parameter free group F, together with another free group whose basis is U1 to UK. A test sequence is a sequence of G to F that stays the identity on F and sends the basis to a tuples that satisfy smaller and smaller cancellation properties. Okay, so this is the simplest example of a test sequence where I don't have any floors. Now, what is it? So one of the properties of having small cancellation property, one of the things that this implies is that actually no word in the AN would be eventually trivial, right? Like small cancellation would break any word.
Sorry, Rizos, could you recall what small cancellation property is?
Yes. So small cancellation is when I have a piece or a subword of a word that appears in two ways, either in the same element or in another element of the tuple, then these have to be very small. It should be 1/n of the total length of the word. So common pieces of the words become small, very small, very small. That's why any word eventually breaks. You cannot have a trivial word satisfied by a small cancellation property tuple. Okay, is that okay?
Yes, thanks.
Okay. So now what what is an example of a Diophantine envelope? I will again take one of the simplest formulas. So it's almost a Diophantine formula, but I have also a negation here. So X is a product of a square and a cube, but of elements that do not commute. Okay. Now, I claim that the Diophantine envelope of this formula is just the free group F together with another free group of rank 2, only I have prescribed an element X inside it, which is going to be, of course, a product of a square and a third power. And in terms of presentation of this group is the same as a free group F free product with a free group of rank 2. Now, of course, the formula that exists u1, u2 such that x equals u1 squared u2 third covers everything. Like it's the whole f. So it covers my formula phi of x. Because I can obtain all elements as a product of a square and a third power. But if I have a test sequence for my tower, now since u1 and u2 would satisfy small cancellation properties, they cannot commute. So again, a test sequence would live in my definable formula. So that's kind of like a minimal example of the above theorem. Right. So if I want to recapitulate here, is that I'm moving to something bigger. I'm moving to an envelope, but I gain something. I gain some understanding of my solution set. Like I gain some geometric intuition here that like test sequences. But apart from understanding my solution set, I need to understand as well how multiplication would work. And that's the hard part, because I could understand that I have two elements in my domain, but if I add them, I do not expect something arbitrary. I expect that my addition would have some connection with my initial elements, but I want to make this more precise. And the way to make this more precise is through implicit function theorems. So an example of such a theorem comes from the core for proving Tarski, and that's Merchliakov's theorem, or the theorem of formal solutions. So what happens here? I'm afraid I will run out of time. But okay, so what happens here? So when I have a system of equations, and I know that in a non-abelian free group, I have that for all x there exists y, that this system of equations is true, then Merchliakov proved that there exists a way to obtain y as a word in x's and the parameters of my free group. So it's kind of an implicit function theorem. So I give you an x, and the y, it's not arbitrary. It's given as a word in these x's that you gave me. Of course, this is a very particular case because sigma is not even a quantifier-free formula, right? Actually, Merchliakov's theorem, as stated here, is not true for even if I add inequalities. There is some version which is true, but not exactly this one. And for me, when I define the plus operation, I need an arbitrary formula, not just a system of equations. And that was definitely the hardest part of the work. So of course, it's not true for an arbitrary formula as it's stated above. But what is true is when for all x, there exist finitely many y, and finitely here, because of NFCP means boundedly many y, then indeed I have a Merchliakov type theorem, but not for all x, but only for test sequences of particular towers. So whenever my formula satisfies these very special conditions, which actually, if you consider this, if y actually would play the role of the sum of my elements. So any group operation would satisfy this property, because for all x, I would have finitely many y's. Actually, when it comes to a group operation, we would have just a unique y, but because I have to take care of imaginaries, I will move from one solution to finitely many solutions. Anyway, and so if my formula satisfies this property and I have a tower and a test sequence that extends to a solution of my formula phi, then there is a tuple of elements in the tower that plays the role of a formal solution, and only for test sequences. So this does not hold for all X, only for test sequence of a particular tower. Right, this is what will give me control of the sum. This is what is going to give me control of the sum of elements. I will see the sum not as an arbitrary word, not as an arbitrary element, but I will obtain the sum as a word of the elements I have added, and that's what allows me to complete the proof, the non-commutative argument in this more general case. Now, as I said, for moving from definability to interpretability, we need to take into consideration imaginaries. So definable equivalence relations. In the free group, we have conjugation plus two more families that we can use to eliminate the rest of the imaginaries. And that's approved by Slil. So these conjugation plus left cosets plus double cosets, and these are families because M denotes like squares, cubes, powers of the centralizers, not Cartesian powers, like subgroups. And for each M, we have a different equivalence relation. So these are families of equivalence relations. So we have this conjugation plus these two families of equivalence relations that eliminate the rest. So through them, we can understand the rest of the equivalence relations. And that's the last piece of the puzzle, understanding imaginaries. So this allows us to move from definability to interpretability. Okay, so I will
just a minute. So basically, the theorem, it allows to reduce every definable equivalence relation to the basic basic source.
Exactly.
Okay.
Exactly. Yeah. There is a definable relation that whenever you give me like an equivalence class, then it analyzes it infinitely many tuples of the basic classes, and it's a class relation. It like whenever like two equivalence classes are the same, then it gives me the same tuple. Okay, so I'm gonna repeat the non-commutativity argument, but now including the imaginary sorts. So I have a first order formula, and now my variable refers to some classes that depend on my equivalence class E. So X is some imaginary class of elements. And again, I have these special formulas that do gain an element when I move to higher rank free groups. Now, the argument is identical with the argument in the beginning, only I have to move my tuple, my honest tuple, I have to move it more than once. I have to move it k times, where k depends on the bound I have of this definable equivalence relation that analyzes my imaginary tuples. So I add my A1 to AK, I got an element Z, and now I plug in the Z, which is of imaginary sort E. I plug it to my relation that analyzes it in the basic sorts. Now, because I can move these basic sorts using automorphisms in this case, like as I could move conjugacy classes, likewise I could move cosets and double cosets using these automorphisms. And because I have a lot of space, I have a lot of permutations. And the main point here that I could choose K, I could choose the amount of my summands after I know E, right? After I know the bound that of my tuples B1 to BL, how many tuples I have. So that's the power I have. And because of that, I could increase the amount of summands. So I could increase the amount of permutations I have in my disposal. So I can increase the number of how much I can move this tuple of basic sorts B. And because I can move it a lot, I just for cardinality reasons, I will end up outside of it. So this would give the contradiction, as I had the contradiction using the normal forms in the first place. And now this leads us to the final argument. So now I do not assume anything special for my formula phi. So I have my formula phi, and it is of some imaginary sort E, or any sort E, even the real sort. And I assign to this formula phi the finite envelope that it's going to have finitely many towers. Now, if all my towers only have a billion floors, like in the picture I have below, then I can prove that phi of x is internal to a finite set of centralizers. This means that the whole solution set is coordinated by centralizers. And because centralizers cannot interpret an infinite field, this passes to phi of x by a theorem of Frank Wagner. Okay, so I can assume that my tower is not, it contains more than a billion floors. And for this talk, I'm going to assume it's hyperbolic in the sense that does not contain a billion floors at all. When it contains a billion floors, the technicalities are much worse than this. So I have a hyperbolic tower in the envelope of phi of x, and knowing the bound on the relation that gives me the basic imaginary tuples, I decide on a multiplet of towers. I decide how much more I will multiply my original tower T to obtain a multiplet of towers, which would be the same tower, the same tower constructed many times. So T1, T2 is the same tower as T1, T3 is the same tower as T1, and I construct the same tower n times around the same bases. And that's actually also a hyperbolic tower. And for a contradiction, I assume that I have a formula that defines an abelian group operation on phi of x. And now I apply the implicit function theorem on this multiplet of towers together with the n summation n summation of my formula, because from my formula O plus, I can define, of course, that I sum up n elements instead of just 2. So I'm applying the implicit function theorem, having my multiplet of towers and my formula psi that gives me the addition. I'm gonna obtain now a formal solution that lives in my multiplet of towers. I would have a formal solution. And now instead of permuting primitive elements, I permute the test sequences, giving different orders of which towers I'm gonna see first, which tower I'm gonna see second, and so on and so forth. This permutation of test sequences permutes actually the formal solution, permutes the variables of the formal solution in a way that it changes it changes enough the solution to obtain the same contradiction as in the case of primitive elements. And that's it. That's the final argument. So this is where one can use this and prove that when X is definable in FEQ, then either it is internal to a finite set of centralizers, or it cannot be given definably the structure of an abelian group. And because of NFCP, this passes to any model of the theory. So NFCP says I can express infinitude. And because the axioms of a field are first order, I can say I'm a field, but I cannot say I'm an infinite field, right? Using NFCP, I can say I'm an infinite field. So no infinite field is interpretable in any model of the first order theory of the free group, not just free groups. And that's the final theorem. I'm over 1 minute, so I'll stop here.
Okay, thank you, Rizos. Thanks, Rizos. Any questions? Okay, I have a question. So if you go through the steps of basically, I would like to understand better, like, what is the difference with this Byron's, yours and Byron proof of definability, like with the proof of interpretability. So is it basically this relation theorem, like this, that you can have, like, so for example, let's just look at the beginning, the final argument.
Yeah. So that's the argument when I include imaginaries. So
basically it's bound on the relation that gives you imaginaries. Like this gives you.
Yes, this gives you the power to do the proof, actually, that I have a bound of the imaginary tuples of basic sorts.
Because you used envelopes, right? The envelopes were used in the proof of non-definability of.
Yes, in the non-definability we used, yeah. But the point is that we can change, because if you take an arbitrary equivalence relation, it's not clear. It's not clear how to in this argument how to change the equivalence class for an arbitrary equivalence relation. But when you have particular, like conjugation, for conjugation, we know. So Slil's result gives us the power to delegate, like
everything to conjugation, basically.
Yeah, basically, yeah, because that was the hardest to make move it.
Okay, and another question. And so, what is with torsion-free hyperbolic groups? Is something?
I think so. Everything should pass through, but I don't want to do it.
But I mean, are there like some results don't exist, or like what?
Results don't exist. Yeah.
I see. Yeah, very interesting. I mean, it's a very interesting result. Any other questions? Okay, so let's thank Rizos again then.
Yeah, thank you very much.
Yeah, and so it's recorded. You can turn off the recording now.